Welcome to springlib.
This is the answer to Chapter 12, problem number 23 from the Smith Organic Chemistry textbook. And in this problem, we're asked what alkyne or diyne yields each set of oxidative cleavage products. So we're basically working backwards here. So we're given the products and we're asked to determine what the alkyne was from which these products came. So remember that when an alkyne is cleaved by ozonylysis, the result, if it's an internal alkyne, the result is going to be 2 carboxylic acids. If it's an external alkyne, so a terminal alkyne, the result is going to be 1 equivalent of carbon dioxide and 1 carboxylic acid. And so all that we really need to do here is join up carboxylic acid to carboxylic acid or carboxylic acid to carbon dioxide. And then that's going to tell us how to piece these molecules together. And so if we look at A, we have an equivalent of carbon dioxide. And so we can just join that up to the carboxylic acid that we have. And so where they join up, that's going to be where the alkyne is. So instead of carboxylic acid and carbon dioxide, this carbon is going to be triple bonded to this carbon. Okay, and so that's A, and that's the way that I would approach each of these. So looking at B, we only have 1 carboxylic acid here, right? And so if we stop and think about this, this tells us that this was a symmetrical molecule. And so it's a symmetrical molecule, the 2 halves of which were joined together by an alkyne. So CH. So here's our first half of the molecule, and it's going to be joined, to exactly its other half. Right. Okay. So CH, CH2, CH3. So I'm actually I'm going to change the way that I did that. I hate using lettering notation like this. So I'm actually just going to draw this like this because I think it's easier. So there's a CH3 there. So then here is our alkyne. Here's another CH3. There we go. This way, it's much less ambiguous about where that methyl group is actually substituted at. So there we go. There's our symmetrical molecule, the 2 parts of which are joined by an alkyne. So then looking at C, we actually have 3 molecules here, 3 distinct pieces. And so 2 of these pieces have 1 carboxylic acid in them. And the middle piece has 2 carboxylic acids in it. So this is just a diyne, right? So we can join each of these up, carboxylic acid to carboxylic acid. And just remember that that's going to be where our alkynes are. And so that's going to look like this. So there's our first piece joined to our second piece. Here is our second piece, our middle piece, joined to our third piece. Okay. And so that's what C is going to look like. So then D is another sort of unique one. So in D, we only have 1 molecule, but it has 2 carboxylic acids in it, 1 at each end. And so this tells us that it's joined to itself. And so this is going to be a 16-membered ring with an alkyne in it. So this is going to be pretty unpleasant to draw. but it's basically going to look like this. So here's our alkyne. Okay. And then straight down. Out, up. Okay, so there we go. There's our 16-membered ring with an alkyne in it. And we know that this has to be the answer because, again, there's only one molecule here, and it has a carboxylic acid on each end. So obviously it was bound to itself. Those two carboxylic acids were the carbons that were participating in an alkyne. And so if you feel a desire to double check these answers, it's easy enough. Just draw a line through the alkyne or alkynes in each, and then draw the products, draw the pieces of the molecule to either side as carboxylic acids, or in the case of A, when it's just one carbon, as a carbon dioxide. And that's a way to double check these answers. And so that's the answer to chapter 12, problem number 23.